Now let us go for the steady flow energy equation. Before going to that, we need to learn about what are the assumptions that are related to the steady flow energy equation. See, the mass flow rate through the system remains constant. So wherever you consider in a particular system or in a particular pipe, the mass flow will always remain constant at any point. Then the second one is fluid is uniform in composition. So when you consider a fluid may be liquid or gas. So when you consider a liquid or gas, it will be uniform in composition throughout. This is the second assumption that we are considering. So the only interaction between the system and surroundings are work and heat. So only interactions are work and heat that we are considering, and we are not considering here any other irreversibilities. Okay, then the state of the fluid at any point remains constant with time. So this is one important point. So steady flow means with respect to time there will be no variation in the state of the fluid. That is what it is saying. Then in the analysis only potential, kinetic and flow energies, flow energy as I told you, the product of PV, are considered. So these are the 5 assumptions on which this steady flow energy equation was derived. Now let us learn about the equation of this steady flow energy. Now for this, let me consider there is a pipe, very long pipe. Let us say it is like this. Very long pipe we have considered. The axis of the pipe is like this. Now let me consider this as the datum or reference line. We have considered this as datum or reference line. So in this pipe certain amount of fluid is flowing, let us say. Now we need to consider a control volume here in order to do the analysis. So for that, let me consider this is the control volume that we are considering, and this is section 1 at this point, and this is 2. Now this section 1 is at a height of Z1 from the datum, and section 2 is at a height of Z2 from the datum. Now let us consider the pressure at section 1 is P1, volume is V1, velocity is C1, and because of the temperature the internal energy is U1 here. Then the pressure at point 2 is P2, volume is V2, velocity is C2, and internal energy at point 2 because of the temperature at that point is U2. So these are the things that we have considered. Now let me say that I am adding Q1 to 2 amount of heat during the process such that I am getting a work output of W1 to 2 during the process. Now according to our first law of thermodynamics, it said that heat and work are mutually convertible and total energy at any point should remain constant. So let us see what is the total energy here. So the total energy at inlet is the sum of potential energy mgz. See, H we are considering it as enthalpy, that's why instead of H I am taking Z here, mgz1 plus half mc1 square, this is the kinetic energy at the inlet, plus the internal energy U1 plus the product of pressure and volume P1 V1 plus the amount of heat supplied Q1 to 2. So this is the energy entering the system. So this will be equal to energy leaving the system mgz2 plus half mc2 square plus U2 plus P2 V2 plus the work done. See, we know that U plus PV is nothing but enthalpy H1 here, and here it is enthalpy H2. Now we can write this same equation like this: mgz1 plus half mc1 square plus h1 plus q1 to 2. So this is equal to mgz2 plus half mc2 square plus h2 plus the amount of work done. So this is what is the expression that we have got. Now let me write this expression just as q1 to 2. So if you write this as q1 to 2, q1 to 2 is equal to mg into z2 minus z1 plus half m into c2 square minus c1 square plus h2 minus h1 plus the amount of work done. So this is the formula that we need to remember here. See, this formula is known to us all, but the major thing where students commit mistake is with the unit conversions here. So let me write the units here carefully so that you can easily remember. So here mass should be in terms of kg, acceleration due to gravity g is in terms of meter per second square, the unit. Then here the internal energy, enthalpy, heat, work, all these should be in terms of joules. All these energy should be in terms of joules. Then velocity should be in terms of meter per second. Z, the head or height, should be in terms of meters. See, and pressure we need to take in terms of pascals. Pascal is nothing but Newton per meter square, that we know, and volume should be in terms of meter cube. So these are the units that we have to consider when we are writing the equation like this. Suppose if you want heat transferred or work done in terms of kilojoules, then this equation will differ. So how does that differ? I will write here. Q1 to 2, if you want in terms of kilojoules, then this will be mg into z2 minus z1 by 1000 you have to do in order to get this in terms of kilojoules, plus half m into c2 square minus c1 square by 1000. You have to divide this also by 1000, plus h2 minus h1. Here enthalpy should be considered in terms of kilojoules and work done. So this equation stands good when mass is in kgs, g is in meter per second square, velocity is in meter per second, z is in terms of meters. So when you have to write this equation, pressure should be taken in terms of kilopascals. Pressure should be taken in terms of kilopascals. Volume should be in terms of meter cube. Internal energy, enthalpy, Q and W, all these should be in terms of kilojoules. Then only this equation stands good. So try to be very much careful with the unit conversions here. See, if mass flow rate is given, mass flow rate means this will be in terms of kg per second. So how do we calculate this mass flow rate? So mass flow rate will be density into area into velocity, or density can be written as inverse of specific volume. So therefore area into velocity by specific volume. Now as in the assumptions it was said that the mass flow rate at any point should remain constant. Mass flow rate is considered as area into velocity by specific volume at point 1. So this is equal to A2 C2 by V2. So sometimes in the questions mass flow rate should be calculated. So when you are calculating mass flow rate, you need to use this particular expression. M dot is equal to area into velocity by specific volume. Now when mass flow rate is given in kg per second, then the same equation will have a little variation where you will get heat transferred and work done in terms of kilowatt if you take internal energy enthalpy in terms of kilojoules. So internal energy and enthalpy also should be taken in terms of kilojoule per second, because when you are multiplying with mass flow rate, then these will become kilojoule per second. So this one you need to remember, and this equation can be written like this: Q122 is equal to mass flow rate. If I take common in all the expressions, you can write like this: G into Z2 minus Z1 by 1000 plus C2 square minus C1 square by 2000 plus small h2 minus small h1. Why we are writing so is we have bought this mass flow rate outside, so we need to consider specific enthalpy. So small h is specific enthalpy, which will be in terms of kilojoule per kg in this particular expression, plus the amount of work done. So this is the formula that you have to use when mass flow rate is given in the question and heat and work are to be determined in terms of kilowatts. So try to remember this. Now these two formulas, mass flow rate and the formula for heat, are very much important, or the steady flow energy equation, so that you can solve all the numerical questions very easily. Now let us go for the applications of steady flow energy equation. So these applications of steady flow energy equations will be helpful for us when we are solving Rankine cycle, vapor compression, refrigeration, air refrigeration, all these. So in all those applications we will use these components. So the first one, let us consider boiler. So if we consider a boiler, so boiler is like this. So let us say certain amount of water is inside the boiler. Now initially this water possesses certain pressure P1, volume V1 and temperature T1. Now because of temperature this will have some internal energy, and we know that when there is internal energy and pressure and volume for a system, then H is equal to U plus PV. So initially this water possesses certain enthalpy, that is H1 we are considering. So the water enthalpy is H1. Now we are supplying to this boiler certain amount of heat such that this water gets converted to steam. Now when this water is getting converted to steam, this steam possess certain enthalpy, that is H2. Now boiler doesn't do any kind of work, and as this is a stationary boiler, you can neglect the variation in the potential energy. Then the kinetic energy, as the velocity of the particles will be very less, initial velocity is almost zero because the water is inside the boiler in a stationary position. So the kinetic energy and potential energy components will be neglected here. So initially H1 is the enthalpy with which water is inside the boiler, and we are supplying certain amount of heat to the boiler such that this absorption of heat is causing the production of steam, and this steam will have a greater enthalpy H2. Now from this, the amount of heat supplied Q122 is equal to H2 minus H1. This is the equation that we have to consider for a boiler. So this is the first application that we are considering. Now let us go for the second application. Second application is evaporator. So this evaporator is majorly used in our refrigeration applications. So when you consider an evaporator, so this evaporator coil is like this, and here is the refrigerated space in which certain amount of products are kept. Now the refrigerant enters into the evaporator with certain pressure and temperature. That means the refrigerator is entering into the evaporator at a lower pressure and lower temperature. So this low pressure, low temperature refrigerant enters into this evaporator coil, and as this is at lower pressure, this will absorb heat from the products that are to be cooled. So that means heat is being absorbed from the products that are to be cooled. So as a result of heat absorption, this low pressure, low temperature liquid refrigerant gets evaporated and comes out as, the pressure remains constant in the evaporator, low pressure, low temperature, which will be slightly more than the initial temperature of the fluid entering, or it may be same also. So that all depends upon the condition at which the refrigerant is coming out from the boiler, whether it is coming in saturated state or superheated state. That we will be discussing later. For this instant, let us say at low temperature only the vapor refrigerant is coming out. So low pressure, low temperature liquid refrigerants enters into this evaporator, absorbs heat from the products that are to be cooled, and as a result of that it comes out as low pressure, low temperature vapor refrigerant. See, this vapor will have little higher enthalpy compared to that of the initial enthalpy with which refrigerant is entering. Now if we apply steady flow energy equation for this case, as the fluid is moving simply because of gravity, we can't consider the kinetic energy variations, and the potential energy variations are also negligible here. So simply H1 plus, why we are taking plus here is heat is absorbed by the refrigerant which is considered as a system. Heat absorbed by the system is positive. So H1 plus Q122 is equal to H2. So from this Q122 is equal to H2 minus H1. See, you may ask a question like this, sir, for both boiler and evaporator we are getting the same expression. What is the difference? See, boiler is used usually for high pressure applications and evaporator is used at low pressure applications. So try to remember, both have the same principle. Liquid should get converted to vapor state, but at low pressure we use evaporator, at higher pressure we are going to use boiler. Now let us go for the third case, the condenser. So if you consider a condenser, so condenser, we know that there is a condenser like this. The condenser coil will be like this somewhat. Now steam is entering into the condenser. There is some cooling water here. So this is the cooling water, let us take, or cooling fluid, whatever you want, you can consider. Now steam is entering. So this steam usually enters into this condenser at high pressure and high temperature. High pressure and high temperature. So let us say H1 is the enthalpy with which steam is entering into the condenser here. Now this steam rejects certain amount of heat to the cooling water. So heat is rejected here, and as a result of that, with same pressure, see, in condenser pressure remains constant as far as our applications are concerned. So as far as our application is concerned, here with the same pressure this will be coming out, and the temperature might be same as this temperature or little bit lower. So for this instant, let us say with the same temperature it is coming out, but this will be coming out in the liquid form. Steam enters into the condenser, rejects heat to the surrounding cooling water here, and as a result of that, liquid formation takes place, and this liquid will have a lesser enthalpy because heat is rejected. See, this condenser also doesn't do any kind of external work here. So therefore we can say H1 minus the amount of heat rejected, this is equal to H2. So from this, heat rejected Q1 to 2 will be equal to H1 minus H2. So this is the expression. So here also we are neglecting the effects of kinetic and potential energies in order to get the expression. So this is the third application. Now let us go for the next application, that is compressor. So you can consider this as air or gas compressor, whatever you want. So this is the compressor, let us say. Into the compressor, let us say air is entering into this compressor with certain velocity C1, and pressure, volume and temperature, all these will be there. Instead of all those, let us say H1 is the enthalpy with which air is entering into this compressor. Now in this compressor, air gets compressed because of the amount of work input that we are giving to the compressor. So we need to supply certain amount of work to the compressor such that certain amount of heat will be rejected to the surroundings, and here the air gets compressed and comes out with a greater pressure and temperature. So the pressure at this point is P1, temperature is T1. At the exit from the compressor, the pressure will be higher and temperature will be higher because of the work addition, and as a result of pressure and temperature rise, there will be increase in the enthalpy to H2 and there will be variation in the velocity to C2. Now if we apply steady flow energy equation for this particular case, neglecting the potential energy components, here we need to use the expression like this: half mc1 square plus h1 minus q122. Why we have considered minus q122 is heat is rejected by this compressor. So heat is rejected by the system, so we need to take negative. This will be equal to half mc2 square plus h2 minus w122. So why we have taken minus 1 to 2 minus w122 here is work input we are giving to the system. So from this we can write the expression. If we want in terms of work or heat, whatever you want you can write. So this is the expression that we need to consider, and remember the unit conversions here. So all the things, heat, work, everything we are considering enthalpy in terms of joules only. That's why we have written this equation. Suppose if velocities are negligible, and isentropic compression takes place, then isentropic compression means we know that heat transferred will be 0 because it will be insulated. Then this equation will be like this: H1 is equal to H2 minus W122. So from this, work done W122 will be equal to H2 minus H1. So the equation reduces like this. So the next component that we have to consider is a turbine. So whatever the turbine, you take gas turbine or steam turbine, anything. So here this equation will almost remain the same. Now see here, there is a turbine like this. So there is a turbine like this. Into the turbine, gas or steam is entering with a greater pressure and greater temperature, and as a result of that the enthalpy will be higher. And this gas or steam, when it is usually coming out of the nozzle, it comes out with a greater velocity. Let us say the velocity is C1 here. Now in the turbine, expansion takes place. As a result of that, pressure drops, temperature drops, and as the pressure and temperature are decreasing, enthalpy also decreases, and there will be variation in the velocity to C2. Now here this turbine will develop certain amount of work output as a result of the expansion of the gases or steam over this particular turbine blades, and due to the expansion there might be some amount of heat rejection to the surroundings. So therefore we can write the equation of turbine like this, neglecting potential energy components: half mc1 square plus h1 minus q122. As heat is rejected, we are taking minus q122. This is equal to half mc2 square plus h2 plus work done. work output we are getting from the turbine. So that is the reason we have got this particular expression. Now suppose if velocities are neglected, and if isentropic expansion takes place, so isentropic expansion means heat transferred to the surroundings will be 0 because this will be perfectly insulated. Then this same equation can be written like this: H1 is equal to H2 plus work done. So from this, the amount of work output that we are going to get will be H1 minus H2. So this is what we are going to get from the turbine. Now let us go for the next component. The next component that we are going to see here is a pump. So when you consider a pump is a device which is usually used to lift water. So let us say from a lower level, let us say at pressure P1 it is there, to a higher level water is needed to be lifted. So then here in order to lift water from a lower level to higher level, we need to supply certain amount of work input to the pump. So that means electrical motor switch that we use in order to lift this water. Suppose if this pump is insulated and there is no heat loss, then what is going to happen is this water initially will have certain enthalpy at inlet and H2 is the enthalpy at exit. Now neglecting the kinetic energy variation and potential energy variations for the pump, here what is going to happen is H1 is the enthalpy with which water enters the pump. This will be equal to H2 is the velocity with which the water is leaving the pump minus the amount of work input that we are giving. So as work input is given, we need to put minus sign here. So work input here will be equal to H2 minus H1. So this is the formula for work input to the pump. See, as fluid is entering into the system and leaving the system, the amount of work input to the pump can also be written as the specific volume of the fluid multiplied by P2 minus P1. So here we are using VDP work. How we are going to get this VDP work, I will be explaining shortly to you. Then the next component that we are going to see here is nozzle. So this is very important, nozzle, because most of the times questions were asked from nozzle topic also. See, nozzle is a device to which fluid will be entering with certain velocity C1 and enthalpy H1, and it will be leaving with velocity C2 and enthalpy H2. See what is happening here in the nozzle, as this is insulated adiabatic nozzle, there will be no heat transfer. So H1 is the enthalpy with which the fluid enters the nozzle, and the kinetic energy is half mc1 square. So this will be equal to H2 plus half mc2 square. So here what is happening in the nozzle is, with the drop in enthalpy there will be increase in the velocity, so or increase in the kinetic energy. Now here we can write like this: half m into c2 square minus c1 square is equal to h1 minus h2, which is nothing but the enthalpy drop. So you can also write this equation like this: C2 square minus C1 square by 2 is equal to small h1 minus h2, because mass, if we remove this, capital H1 minus h2 can be written as m into h1 minus h2. So mass gets cancelled on either side, and you can write the nozzle equation like this: C2 square minus C1 square by 2 is equal to h1 minus h2, where the velocity is in meter per second and enthalpy is in joule per kg, not kilojoule per kg. It will be in terms of joule per kg. Suppose if enthalpy is in kilojoule per kg and velocity c is in meter per second, then you should write the expression like this: C2 square minus C1 square by 2000 is equal to h1 minus h2, and from this C2 will be equal to under root of C1 square plus 2000 into h1 minus h2. So this is the exit velocity formula. Now suppose if C1 is negligible, compare it to C2, then C2 will be equal to simply 44.72 root of h1 minus h2. So root of 2000 is 44.72. So from this we are going to get here. Suppose if friction coefficient is given for the nozzle, friction coefficient K is given in the nozzle, then here C2 will be equal to 44.72 under root of K into h1 minus h2. So this is the expression that we need to consider for the nozzle.